Okay, so let's continue our discussion related to circuit analysis. So today we'll go over some of the things that we have already done, and we'll look at those things, techniques using an example. So we had seen that a technique called nodal analysis, where we try to determine the node voltages, and then another technique where we identified meshes inside the circuit and assigned the mesh current, and we determined that those were the unknown variables. And then we looked at a technique which we called as based on reusing results that had been derived and verified earlier, results like series and parallel equivalent circuits, current and voltage division, delta Y transformation. Then we had looked at a technique whereby called the superposition principle, whereby we could evaluate the response of each independent source separately and then add up the results to get the total response. And then we had seen the concept of Thevenin's equivalent circuit, where a complicated circuit could be transformed into a voltage source and a resistor, and Norton's equivalent circuit, where that circuit could be transformed into a current source in parallel with a resistor, as long as the circuit was linear. And then as a special case of Thevenin's and Norton's, we looked at source transformation, where a voltage source in series with a resistor could be transformed into a current source in parallel with a resistor, and vice versa. So let's look at some of these things using a concrete example. So this is the circuit that we will analyze, and the circuit has one independent source here, a voltage source, and this is also a dependent voltage source which depends on this current I here. So first thing what we'll do is we'll try and analyze the circuit, obtain voltages and currents using mesh analysis. So we identify the mesh. There's a mesh here. We identify a current here. We identify another mesh here, and we identify another mesh here, right? Three meshes are here. We assign them currents, I1, I2, I3. And then for each one of those meshes, we write down the KVL. So let's write down for I1 here. All the meshes, the currents have been taken in clockwise direction, so we go clockwise in the direction of the current. So we start from here. So we write down 2I1, and then there is a voltage drop of 10 volts, and then when we come here, then it is I1 minus I2 into 4 here. So that's the first equation. For the other one, let's say we start from here, clockwise direction. So we start here, we go up, and as we go up, the drop is 4I2 minus I1. Then when we come here, we are gaining a voltage, so minus 5I, and then we go down, we have a drop of I2 into 3, so that's equal to 0. And then we write down the third equation. We start from here, again we go clockwise, 6I3, and then we have 5I, and then we have a voltage gain here, so we put in minus 10 equal to 0 here. And the other thing we know, this is a dependent source, so it's 5I, so I we can write it as I is nothing but, if we look at this current here is nothing but I1, minus I1. So we have these equations, and now what we have done is we have taken the circuit and transformed it into a set of equations. Now it's a set of linear equations which we can solve to get these currents. So if my analysis is correct, then I1 is minus 1.5, I2 is 0.217, I3 is 0.4 amperes here. And so you obtain all the mesh currents, and through the mesh currents, of course, you can get any of these currents. For example, current flowing in 2 ohm resistor is simply equal to I1. Current flowing in 6 ohm resistor is simply I3. Current flowing in 3 ohm resistor is simply I2. If you want current flowing in the the battery here, so that's going to be this is trying to force a current I1 here, and this is trying to force a current I3 here. So the net current in the battery is going to be I1 minus I3. So like that, we can determine any current, and voltage also, if you're interested in voltage V2. So V2 will be equal to 4 I1 minus I2. So that's equal to minus 6.95. So that in essence is what mesh analysis is, a well-defined systematic method of transforming a circuit into a set of equations and then solving them up to get all the answers. All right, let's look at the nodal analysis. So same circuit we'll analyze using different techniques. So in nodal analysis, we identify all the nodes here. So in this case, to begin with, one of the circuit already has a ground. So what we can do is we can take this particular node as a reference node, and it has a 0 potential here. Now, if we look at it, if we try, there is a voltage source between these two, and we saw that when you have a voltage source and you will try to write KCL at 1 or 2, you will have a problem because we don't know what the current flowing through the voltage source is. So you may want to combine these two into a super node, but then 2 is also connected to 3 through a voltage source. So again, we will not be able to write KCL here. So we can combine 1, 2, 3 into one large super node here. And to this super node, then we can write down the KCL. So let's write down KCL for this super node here. So again, we'll look at all the currents entering and leaving this particular super node here, the surface of the super node. So the equations are here. So minus V1 by 2. So the current, for example, entering this particular node here, current going up into this particular surface. So that's going to be 0 minus V1 by 2. So that's why minus V1 by 2. So current going up at this point. Current coming from the top here. So this current entering this particular surface. And what is that current? Well, that will be V3 minus V1 divided by 6. So that's the current entering here. And similarly, we have to look at all the currents entering and leaving. So there is a current entering here from this side here, from the bottom. And that's equal to 0 minus V2 by 4 ohms here. So that's why this minus V2. There's a current entering from the bottom here also. So that's minus V3 by 3 here. And then there is a current, let's say, coming from the top here. And the current coming from the top is V1 minus V3 by 6 here. So we've added up all the currents entering, leaving, and the sum is equal to 0 here. And the other equations that we get are basically the relationships due to the voltage source here. So V1 minus V2 is 10 volt. V3 minus V2 is 5 times I. And I is nothing but, according to our this thing, V1 by 2 here. So I is V1 by 2. So we can take this equation V3 minus V2 equal to 5I, and that becomes 2.5 V1. Okay. So we have basically now one equation here, second equation here, and a third equation here. We can solve them up and get the answers that we're looking for. For example, if we are interested in node 2, we will get V2 equal to minus 6.95 volt. And similarly, you'll get, once you get V2, note that you will get the value of V1. And once you get the value of V1, you know the current here. So you know this particular voltage source also, right? So you'll get all the all information about this circuit here through this nodal analysis. We could have done this problem in an alternative way. In a circuit like this, we were given this node as a ground. But then note that it's only a reference. And what we can do is we can choose a reference, even though it's written ground here, we can choose the reference any way we want during the analysis, right? So temporarily what we can do is, okay, so these are all the 4 nodes here. Temporarily what we can do is we can forget about this ground node here. And let's say we can choose whichever node we want as reference, as 0. So in this case, we see that if instead of this as a ground, if we choose 2 as a ground here, right? So if we choose this as 0 volt, then what happens is, of course, this voltage becomes known, is our reference, 0 volt. Then we know that V1 is 10 volt, and V3 also, we can straight away write V3 is equal to 5 times I, right? So V3 is 5 times I, and of course I is equal to 10 minus V4 by 2. So this is 10, and we are saying this is V4, 10 minus V4 by 2 here. So temporarily what we are saying is we're removing the ground, and we are saying let's choose whichever node we think would help us in solving the circuit. So temporarily we are assigning, let's say this is 0. And thereby, what we have is we know V1, we know V2, and we know V3 also. We have an expression. So what we can do is we can write KCL at node 4 now. Okay, so node 4 for us is unknown right now, because once we have removed this and made this 0, so KCL at node 4. So KCL in node 4, we look at all the currents that are entering this node 4. So there's a current which is entering here. So 10 minus V4 by 2. There's a current entering from here, so 0 minus V4 by 4 ohms, and there's a current entering from here, V3 minus V4 by 3. So, so we have one equation, and V3 we already know here in terms of V4, so we can plug it here and solve it. We'll get V4 equal to 6.95. All right, but then we have to go back to our original circuit. So what we can do is, note that V4 that you've obtained 6.95, we can write it as is with respect to node number 2. So we can write it as V4 minus V2 is 6.95, or V2 equal to V4 minus 6.95. And if we go back to our original one, we can put V4 equal to 0. So we get a value of V2 equal to minus 6.95. So we restore the ground here, and then we write V2 with respect to V4. That's what the meaning of ground is. So V2 becomes minus 6.95 and V4 is 0. So similarly, we can find out what is the value of, let's say, V1. So V1 we know was 10, and V4 we just found out was 6.95. So V1 minus 4 is 10 minus 6.95 equal to 3.04. So V1 we can write as V1 equal to V4 plus 3.04. Now V4, we can restore V4 back to ground, and then V1 becomes 3.04. So the value of V1 with respect to V4 is 3.04. So when we say value of V1 with respect to V4, we are saying V4 is taken as ground here. So that becomes 3.04. So what this is saying is, even if a ground connection is given and you're not happy with this ground connection from the analysis point of view, temporarily you can forget about this ground and assign a reference node the way you want, the one which will help you in analysis. Do all the analysis. So what you will get is, you'll get all the voltage with respect to 2, and then what you can do is you can transform it back to with respect to reference number, whichever was the reference earlier, right? So this is what we did here. Okay, so let's solve this circuit, same circuit, using Thevenin's equivalent circuit here. All right. So let's say we are interested in the voltage across node 2 here. So in Thevenin's equivalent, you have to define which node you are really interested in, and then across that particular node you build the Thevenin's equivalent, right? And note that our when we build Thevenin's equivalent, we'll get the voltage across node 2, and but we will not get voltage across, let's say, node 3, because Thevenin's equivalent then would take the rest of the circuit, transform it into a simplified circuit, which will give us the real value of the voltage at 2, but it doesn't give us then anything else. But in this circuit, as you know, that if I get node 2, then I will get node 1 also, because there's a voltage source attached. And if I get node 1, then I know this current here, and so I will be able to obtain everything else also. Okay, so let's build the Thevenin's equivalent. So what we do is, we remove this particular element. We are going to build Thevenin's equivalent between these two nodes here. And in Thevenin's equivalent, the first thing that we try to do is find out what is the open circuit voltage here. Okay, so between these two nodes, we've already opened it. So open circuit voltage we need to find out. And we can take a loop like this here. We can apply a mesh method. The moment you open it up, this whole thing becomes a mesh here. And you can apply a KVL around this one. So note that the current in this one is basically I. We can assume that the current circulating here in anti-clockwise direction, let's say, is I. So you can start from here. There is 3I, and then there is a drop of 5I, and then there's a voltage gain of minus 10, and then there's a drop of 2I here. So we get this equation here. And we solve it, we get I equal to 1. Right? I equal to 1 here. And once you get I equal to 1, then you know V1 equal to 2 volts here. And once you know V1, then you can find out what is the value of V2, which is basically equal to minus 8 volt. And that's nothing but the open circuit voltage here. So we obtain the open circuit voltage very quickly by solving this. Basically, the moment you open it up to find out open circuit voltage, note that the circuit becomes very simple. It's basically boils down to a single mesh circuit, and the calculation becomes very simple for open circuit voltage, minus 8 volt. The next thing, because there's a dependent current source, what we try to do is we have to find the Thevenin's resistance, and we try to do that by short circuiting the two terminals here. And yeah, I equal to 10 by 2, 5 amperes here. Okay, so let's remove this, let's short it, and our goal now is to find out what is the short circuit current. And the short circuit current we can find out by let's say by applying a simple nodal method, by doing a KCL at this particular node here. Okay. Note that even though the node voltage is known, but that doesn't mean that you cannot, or it's not useful to do a KCL at this node. So when we do KCL at this particular node, we sum up all the currents entering this particular node, and it's equal to 0 here. So entering from here is 10 by 2. From this side is ISC, and from here is the current that is entering from here. Note that we need the voltage at this particular node here, and the voltage at this particular node, because this is 0, the voltage at this particular node is 5 times I, and that's why we had calculated I, which is 5 amperes here. So the voltage at this particular node becomes 25 volt. So that's why the current coming from here is 25 by 3. So we solve this and we get ISC, the short circuit current, is minus 40 by 3. So we have found out open circuit voltage and we have found out short circuit current. We can take the ratio of the two and we get the Thevenin's resistance, which is 3 by 5 ohm. So now between these two terminals we can build the Thevenin's equivalent circuit. Oh, this is the Thevenin's voltage minus 8 volt. This is 3 by 5 ohms. And so this is the whole circuit here. And then we add back our original resistor, which was 4 ohms. We wanted voltage across this. So we can use voltage division. Voltage across this resistor here, V2 will be minus 8, 4 by 4 plus 3 by 5 equal to minus 6.95. So note that this is the value that we had obtained also using mesh method or nodal method. And Thevenin's equivalent obviously also gives us the same value here. Now, many times students have or in general, all of us have, this feeling of how come a complicated circuit like this can be transformed into only a voltage source and a resistor. So in the previous lecture, we had stated that, and in the derivation of Thevenin's voltage and Thevenin's resistance, it was implicit as to why the circuit can be transformed like this. But let's look at it from another angle here. Okay, so basically Thevenin's equivalent is saying, we had this diagram. What it's saying is that when you have a linear circuit consisting of resistances and independent and dependent sources here, and across a pair of terminals, you could replace this by a Thevenin's voltage and a Thevenin's resistance here. So the issue is, why are we able to do that? How come this complicated circuit can be replaced by one single voltage source and one single resistor? Well, the answer to this is in this important phrase here, because it's a linear circuit. And so let's explore this. Because it's a linear circuit, so for the time being, let's say this is the voltage here and this is the current here. Let's say current going in and the voltage is over here. So please note that what we are saying is that this circuit here, this part of the circuit here, is equivalent to this part from the terminal point of view. Okay, we're not saying that inside everything, because this circuit doesn't capture what is inside it, right? So it's only from the terminal point of view we are saying that this VTH and RTH has the same terminal characteristics as this complicated circuit. Anyway, so the point was that it's only when the circuit is linear that we can do it. So linear circuit, which means what? That the relationship between current and voltage is linear. A linear circuit made up of linear elements will have linear current voltage characteristics. So let's show a typical linear characteristics. So let's say this is current and this is voltage. Because it's linear, we can draw it with a straight line like this here. Okay. And so if this is a straight line, so let's identify these 2 points. So this will become 0 current. So this becomes the open circuit voltage here. And this one, 0 voltage, which means we short it out. And so this we call as the short circuit current. Note that the direction of short circuit current that we had taken was going down here, right? So that's why minus ISC here. Right, so so this is a linear circuit, so it can be described by a straight line like this, and there would be some open circuit voltage, some short circuit current. So of course the slope of this particular line we can write down. The slope will be VOC minus 0. We take this point here and we take this point here. So VOC minus 0, 0 minus ISC. So it's a ratio of voltage and current. So we define the slope equal to some resistor here. RTH, we have just chosen the symbol RTH. You can write anything here. So, but it's a resistance RTH. So, so let's say the slope of this particular line is the inverse of the slope of this particular line here. Okay, because we have plotted I versus V. So inverse slope is RTH here. Now we can write the general expression for this straight line. The general expression for the straight line, if I choose any point, let's say where the voltage is V and I, we can write V minus VOC over I minus 0 is equal to RTH here, right? So a general expression we can obtain, and we can write it like this: V equal to VOC plus I into RTH. So this line here, which is the IV characteristics of this particular circuit, can be expressed in this form. This is the equation of a line here. And this equation of a line, this expression here, we can show it like this here, in the form of a circuit. V equal to VOC plus I into RTH. So instead of VOC, we have written VTH here, and RTH we've already seen, VOC by IC. So what we have seen is that this circuit, because it's linear, it can be described by a straight line. The straight line can be described in terms of VOC and RTH, and therefore this is the equation for a straight line, which in the form of a circuit can be expressed like this: a VTH and an RTH here. So that is the reason why we are saying any linear circuit with a linear current voltage characteristics can be described by these two elements here, VTH and RTH. They are sufficient. If it were not a linear circuit, then we couldn't have done this. Then the equation of this, whatever curve we would have obtained, would have been far more complicated, and two elements like this wouldn't have been enough to describe that particular circuit. We could also note that we can also write the line of this particular, the equation for this particular line, by taking any voltage here and taking the other point here, V minus 0 I minus ISC equal to RTH, and we can write it I equal to minus ISC plus V by RTH. And short circuit current, let's use some other symbol here, equal to IN, and then this, note that we can describe it in this form here. So it's the same equation, rewritten, equation of the same straight line, same circuit, but rewritten in this particular form. And when you write it in this particular form, well, you can express it in a circuit like this here, where Rn is nothing but RTH here. So we are seeing that if the circuit is linear, described by a straight line on the current voltage characteristics, then this is a general representation of that particular circuit here from the terminal point of view. This is important. From the terminal point of view, this circuit IN-RN, composed of IN-RN, is indistinguishable from whatever is inside it. So that's the basic idea behind Thevenin's and Norton's equivalent circuit here. All right, so let's stop here.